This is the Math Olympiad problem I want to solve with you today. The task is that with a given integer sequence, an, you can see here, we have to find the smallest integer k for which this inequality holds. If you want to write the product informally, you could also do it like this, which is the way we are going to write it from here on out because it's just more obvious what's going on. Today we will actually solve a more general version of this problem, where the 4 can be replaced by any integer m, as you can see here. But first let's concentrate on the sequence an itself. We will first simplify the polynomial and embed it in the cube root. Okay, so let's algebraically manipulate it. We can factor out a 2 squared from those left two terms here to get 2 squared times 2 plus 1. And for the right two terms we can factor out a minus 1 to get minus 2 plus 1. Next we can factorize the term and use the difference of 2 squares, 2 squared minus 1 squared, to factor it even further into 2 minus 1 times 2 plus 1 times 2 plus 1, which is this factor from here. And to get our fully factorized expression, we just put those together in a square to get 2 minus 1 times 2 plus 1 squared. So now our sequence looks like this. Now we can insert this representation into our product down here, which is the thing we actually want to evaluate. That is the inequality we get. Let's group like terms. We put the fractions, marked in green here, into one bracket and the roots into another. Now we analyze this expression. The yellow part can be put under one fraction, which leaves us with 1 over k factorial, because this is just multiplying all the numbers from 1, you can leave out 1 because it doesn't change anything, up to k. Next we can also put the cube roots under one big root, like this, and we group squared terms into one bracket and the other terms into another bracket, as you can see here. Now let's first focus on the purple part again, which is just 1 times 2 times and so on up to k minus 1, so this is just k minus 1 factorial. And now the red part, it's 3 times 4 and so on up to k plus 1 and all that squared, because we can put the square on the outside. And to get a factorial up here, we have to insert the missing 1 and 2, which we have to divide by to make this equal. So we have to divide by 4 basically, to get our final term of k plus 1 factorial squared over 4. Now we can put it all back together. This is the inequality we now just have to manipulate algebraically again. Here's our inequality. We can cube both sides to get rid of this cube root, and then we multiply it by 4 to get rid of this fraction. Now we put everything under one big fraction like so, and multiply the top and the bottom of this fraction here by k, so that k times k minus 1 factorial can be written as just k factorial. Also, this k plus 1 factorial is just k plus 1 times k factorial, and if we plug that in, we get this term on the top, and k factorial to the third is here in the numerator and in the denominator as well, so we can just cancel those out. And then we get k plus 1 squared over k is bigger than 4 times m to the third. We cancel the k again by multiplying by it, and we get k plus 1 squared is bigger than 4 times m to the third times k. And if we multiply out the square like so and get this on the other side, we can actually use just the square polynomial formula to solve such square inequalities, which is just the same for equalities. I have written out the steps here, but I won't go into them in detail because they're just completing the square. So our final result is this inequality, which we are going to look at now. There's actually still a plus minus in this inequality, which means it represents two inequalities, the one with plus and the one with minus. But because in this case a square root cannot be negative, the right value here has to be smaller than the left value, because you subtract something positive from the same term, 2m to the third minus 1. So this has to be smaller than that. But that just means that this right inequality is abundant, because we can just use the one with the plus, because both can only be true if and only if this one here is true. This is the inequality we just got, and let's look at the root term of it. To analyze this, we have to take into account this inequality, which has to be true. This part of the inequality has to be true because those are consecutive squares, and if this would not be true, that would mean their difference is less than 1, which cannot be true for the squares of any whole numbers which are consecutive. So this has to be true. The right part of this inequality has to be true because that number here is just 1 bigger than this, because it's the same square, but there's a minus 1 here additionally. Now if you take the root of all of these terms of the inequality, you get this inequality, which tells you that the root we want to know about lies between those two integers, 2m to the third minus 2 and 2m to the third minus 1. Those are consecutive integers. So that just means that if we substitute the lower bound into the inequality, it would just have the same effect of removing the fractional part of this root. And because k is an integer, this won't have any effect on the value of k. So now we group like terms in this inequality after we substituted the lower bound for the square root. And then we get k is bigger than 4m to the third minus 3. But because k has to be an integer, it's just 1 bigger than this. So 4 times m to the third minus 2. Let's substitute m equals 4 to get the answer to our original question. This implies that k has to be equal to 254, and that's the smallest k. Okay, so let's test it. I wrote a small Python program to check if this is the right answer. The first function a of n is just the sequence an. Then we have the prod function, which calculates the product up to k terms according to the problem statement, which is this function here. So now let's see what 1 less than our answer, meaning 253, gives as an output. It's just shy of 4, 3.9948 approximately. And now we'll let it calculate the number for k equals 254, which should be over 4. And it is. It outputted about 4.0000205. But let's also try it for another example. M equals 6. The answer for k is apparently 862. Let's run through the program again. Firstly, 1 less than the actual answer, 861. It's again just less than 6. And 862, just over 6. So the inequality holds for the first time exactly on the predicted value of k. Our final answer to what the smallest value for k is for which the inequality holds, thus is 254. We even solved a more general version where the product is bigger than any positive whole number m. I kinda like this problem because it connects the continuous real numbers and the concrete whole numbers. You multiply a lot of rooty expressions and still can say something about when the product is bigger than a certain whole number, but not, at least by this method, when it is bigger than any real number. You could also widen this derivation to include real numbers, but in my opinion that solution is less beautiful. You can try out to find out yourself what the value of k has to be for any real number as an extra puzzle, but be warned, it involves some casework. Now that we have solved the problem, let's also shortly look at the sequence an itself. When we consider its limit as n goes to infinity, we see that because in the top term, inside the root, the n to the third term dominates, we have following. If we now take the cube root and simplify, we get that the limit is actually 1. This means that the sequence, which is the product of these, could actually be convergent. But what we have also proven with our result is that no, it is divergent, because for k equals 4 times m to the third minus 2, the sequence is always bigger than m, which is why it tends to infinity as k goes to infinity, because you can always find a value for which it is bigger than any integer, which was just another interesting thing in my opinion. Anyways, thank you for watching, I hope you enjoyed it, and see you.